Welcome back. In this video we're looking at scales and scale drawings. So the learning intentions for today is that hopefully by the end of this lesson you will be able to calculate the actual length of an object if I give you its scale. You'll be able to draw an object to a scale given, and you'll be able to convert between a drawn length and a real length of a scaled image, again if the scale is known. And lastly, you'll be able to calculate what the scale of an object or image is if you know the drawn and the real lengths of it. So firstly, what is a scale? A ratio we've talked about is a comparison of two quantities. A scale, however, is a ratio between two sets of measurements. So very, very similar to what a ratio is. And it's really just that, but we're specifically talking about converting one measurement to another measurement to get a scale. When we make a scaled copy of an object, the original and the copy have the same proportions. So how much we scale a certain length of an image is equal for every part of the image. Otherwise we'd have this really deformed picture with like a giant head and a tiny body and things like that. And we just don't have that. A scale drawing or a model is a drawing that uses a scale to make the object generally smaller, which is a reduction scale. Sometimes we can do it to make the object look larger than the real object if the thing is already really small. But it's definitely more common to see that reduction scale. An example is things like scale model kits. So you can see the plane here, the tornado, it has a 1 to 32 scale. So that's a reduction scale. That's saying for every 1 unit in the real world, it would be 32 units of it. So what I want you to do is pause it, have a chat with your partner, maybe even your team. Think about as many examples as you can that would use a scale besides just like a model kit. So pause the video, have a chat. Come back to it. Now we're going to look at scale drawing specifically. So the scale drawing allows us to draw a large object on a smaller scale while still keeping it very accurate and keeping all of those proportions. All of the scale drawings must have the scale written on them for other people to then know how big is this thing in the real world. And they're usually expressed as a ratio. So when we write it as a ratio. An example of this is that the ratio of 1 centimeter to 100 centimeters, that is the scale of a drawing we might do. It means that for every centimeter I measure on the page, in the real world that's 100 centimeters or 1 meter. So I know if I measure a length of something and it's 4 centimeters, in the real world that length would be 4 meters. So I can scale it up. Some examples of scales that we see all the time. Some of these you might have already just discussed with your group. When we look at things like Google Maps, Google Satellites, you notice down in the bottom corner, there's this little 10-meter line. So that's telling you that this line here is 10 meters. So if you measured the length of that on your computer, or you screenshot that and then drag it over here, you can go, alright, well that would be approximately 10 meters, approximately 10 meters. I would guess that the width of this building is somewhere around the 50, 60 meters. If you say each of those is 10, that's 40, maybe about 50 plus a little bit. So you've got a scale there. Another example which is very common is floor plans and drawings of houses. Again, you'll see down here they've got a scale. They've even told you here it's a 1 to 100. So 1 centimeter equals 100 centimeters, just like we saw before. So we can use that as our scale. Another example is just drawings and things like that. So here we've got a real horse, it's 1.5 meters high or 1500 millimeters. They've drawn it at 150 millimeters high and they've told us the scale is 1 to 10. So for every unit of this picture, it is 10 times that size in the real world. So that's another example. Another example that we see very, very commonly is on a map. Maps obviously cannot fit the entire world on a piece of paper without scaling it down. And therefore we then need to know what that scale is. If I'm going to walk from number 6 here to number 5, it's pretty important that I know how far that is. If I look at my scale and go, wow, that's 1 to 24,000. So if I go, that is 1 centimeter, which it's clearly not, that's actually equal to 24,000 centimeters. So suddenly I look at the scale and be like, alright, maybe I can't walk from 6 to 5. That's maybe a bit too far for me. So it's really important to have this scale. And they also give us this additional stuff, which is basically a length for kilometers. So if here to here is 1 kilometer, you can say, alright, so roughly each square is a kilometer. So in a straight line, that's maybe 1 from 5 to here, and then 3/4, so maybe it's like 1.7 kilometers. in a straight line, but I've obviously got rivers and stuff like that. So the scale is really useful. Another example we see it is when we graph things, we often use scales and ratios. So in this example here, we're looking at air-fuel ratios of engines, and in this case, they're comparing horsepower to an air-fuel ratio. And I'm going to talk about this stoichiometric ratio thing a little bit later, but they're using this ratio between air and fuel ratios and horsepower to find things like the optimum power curve, to create the most powerful engine you can, as well as improving your economy and not using too much fuel. So when we write a scale, it's written in the form of drawn length to actual length. So the 1-to-1 scale factor here means for every length that is drawn, the real one is the same length. So that would actually be an image that is the actual size of the thing. Here we can see this would be an example of it. So this is a 1-to-1 scale of a cricket. This is a 1-to-2. So for every 1 centimeter, the thing is 2 times bigger. And this is a 2-to-1. So I've actually drawn it bigger. Every 2 centimeters on the cricket is only 1 centimeters in real life. So it's always what we've drawn first, then what the actual length is second in the scale. Quick question for you. I've got a model of a dinosaur here on the left. Its scale is 1-to-12. That means that for every how many centimeters of the model, the real size would be how many centimeters? Hopefully you've said 1 centimeter equals 12 centimeters. Good. If not, make sure you understand where that's coming from, that the ratio is always drawn to real, and that's where the answer comes from. Next question. The head on the dinosaur is 8 centimeters long. How long is the head of the real dinosaur? So have a quick think. The answer is 96 centimeters. So again, if it's 8 centimeters drawn, then we multiply it by 12 to get the real length. We get 96 centimeters. So it's a pretty big head, a 1 meter head. Now if we want to find the drawn length. So we've got the image, we want to know how big would it be drawn if I knew the scale. Here we have a living room that's 4 meters long, and we've been told we want to redraw that living room on a scale of 1 to 50. What length are we going to draw on the piece of paper to draw out a living room? The trick is that the drawn length is equal to the actual length divided by the scale factor. So basically the opposite of what we've just seen before. Actual length divided by scale factor. Sorry if you just picked up my dogs barking in the background. My garbage was just getting collected and the dogs went bunta. So for example, if we had a drawn length of 4 meters, 400 centimeters, we would divide that by the scale of 50. That means I would draw a line of 8 centimeters in this case. So actual divided by scale gives me the drawn length. So make sure you write that down in your notes. If we said the distance between two towns, let's just call them town A and B on a map, is 15 centimeters, and the scale on the map is 1 to 500,000, how would we calculate the actual distance between the towns? The rule for this is that the actual length is the drawn length multiplied by the scale, which you've kind of already done in your head before when we said every centimeter is equal to 500,000 centimeters. What we're really doing is whatever number we've got here, we multiply it by 500,000. So that's what we're doing. Whatever the drawn length is, you multiply it by 500,000, you get your length. So in this case, we get 7,500,000 centimeters. Let's make that a little bit cleaner. We get 75,000 meters, or 75 kilometers between the two towns. So the actual distance is 75 kilometers using that scale. Challenge questions for you is calculate the scale of the following images. In this case, I want you to round it to the nearest whole number. So here we've got the Hubble Space Telescope. It's 13.2 meters. It's been drawn with a length of 4 centimeters. Calculate the scale of this drawing and repeat this for the other questions. Answers will be up in 5 seconds. So pause the video. Once you complete, I'll give you the answers. Okay, answers are here. So in this case, I've said Hubble Telescope 1 to 330. You can see I've done the real length divided by the measured length. Make sure the units are the same. That's the most common mistake people make, is the units need to be the same. So I've used meters for this. Falcon Heavy, 70 meters divided by 0.03 meters. I get a 1 to 2,333 scale. The Moon, even bigger. I get a 1 to 65,547,169 thousand scale. That's pretty huge. That's a hell of a scale. And my Astronaut is a 1 to 34, so it's a much more placid little scale there we're working with. Now we're going to change it a little bit. In this case, I want you to draw the actual length, calculate the actual length of the images given their scale. So the Noisy Cricket, you're told the scale is 1 to 10 and it's drawn with 6 centimeters length. The TARDIS is a 1 to 45 and it's drawn with 6 centimeters. Roger the Alien is a 1 to 25 scale and is drawn with 5.4 centimeters. And the Infinity Gauntlet is a 1 to 8 scale drawn at 6.1 centimeters. So calculate the actual length in the real world of these objects. Answers will be up in 5 seconds for you to check. Answer time. Noisy Cricket, 60 centimeters long in the real world. That's gigantic. For anyone that's seen the first Men in Black, the thing is tiny. Obviously, I made this question up. It is not 60 centimeters. It's more like 6 centimeters. Roger is 1.35 meters tall, or 135 centimeters. Seems about right. The TARDIS, 2.7 meters. Plausible. Yep, I could fit in a 2.7 meter TARDIS, so I'll take that. And the Infinity Gauntlet, clearly something has gone wrong. The thing is 4.9 meters long, so either Thanos is an absolute giant, or I didn't check my maths before I did this, and the answer is complete nonsense. However, the answer is correct mathematically. So 48.8 centimeters, or, wait a minute, I see what I've done. It is not 4.9 meters, it's 48.8 centimeters. That does not equal 4.9 meters, Mr. Riak. Bad. Ignore this. 48.8 centimeters is the length. That's a bit more realistic. It's still a gigantic hand. For anyone that's got a ruler nearby, 30 centimeters is this. The length of my head plus a bit. It's well beyond that. So it is a gigantic gauntlet. But mathematically, we're still good. So just ignore Mr. Riak forgot how to convert centimeters to meters here. Let's leave that bit out. Next thing we can look at is this concept of direct proportion. So if we have a look at these two rectangles side by side, we would say that they are similar because they actually have the same ratio. So on this one, you can see I've doubled the length. Here I've also doubled the length. So we would say these are proportional. Another word for that mathematically is to talk about similar. And later on, in a later topic, when we do triangles, we'll see this concept of similar triangles, where they are proportion to each other. So we could say that a 2 to 3 ratio here is equal to a 4 to 6 ratio here for a bigger rectangle. And that's what we saw before when we scaled up or we factorized ratios. So if we wanted to convert from one ratio to another, we just multiply both ratios by the same constant, which in this case is 2 because they've doubled, and we get our new rectangle. So we would say that they are directly proportional in this case. If this was our rectangle here, we would say that x is directly proportional to y. And in physics, this comes up a lot. Directly proportional means that if I increase one, the other will increase by the same amount. They're linked to each other. So if I double x, y will also double. Let's look at some flight ratios. So given that our topic is primarily around flying and the engineering of flight, I want you to consider the Boeing 737-200, which is crudely drawn below. Firstly, I want you to convert the percentages into ratios in the table below, given the things that you have been given. So the ratios in general for a plane are that the fuselage, which is just the body of the plane itself, the aspect ratio is the wingspan squared divided by the wing area, which is about a 6 to 8. So for the wingspan squared, which will be R1, it needs to be, so like a 1 to 6 or a 1 to 7 or a 1 to 8, something in general like that. You don't need to calculate that one. I've left that out. That's a little bit more complex. However, the fuselage needs to be between 67 and 75 percent of the wingspan. So we need a ratio of, if we go smack bang in the middle and we say 70, we need a 1 to 70 ratio of fuselage to wingspan. So that's really useful to think about later when you start designing some planes. The horizontal stabilizer needs to be between 20 and 25% of the wing area, and the vertical stabilizer needs to be between 40 and 50% of the horizontal stabilizer area. So what I want you to do is use the image you've got here. Treat this as your scaled image. So you can make some approximations here, but if we know that the fuselage body here is 73.9 meters long, and we know that the horizontal and vertical stabilizers need to be between 20 to 25 and 40 to 50, I want you to write what would the ratio for these things be. If you want to go one step further, give me the ratio, but also tell me what would the length be using that ratio. So that's a real world example of calculating a length. If I said, I've got a plane, this is how big the body needs to be, what kind of wings do I need, or what kind of stabilizers do I need for the vertical and horizontals, you could then go, oh, well, that's easy. I can plug in a ratio and I can give it to you. Maths, big brain. So, what we're going to do, use the specifications for the plane below. I want you to verify if those ratios are in agreements with the recommendations that were given. So here you've got a bit more detail. I've given you the wingspan, I've given you the tail height, things like that. I want you to just check, are these dimensions agreeing with the recommended specs for the average plane, or are they a little bit out? So have a go at figuring out some of the solutions to these questions. Next, we're going to look at this other concept of ratios. Something called an aspect ratio in tech language is the measurement of an image's width to height. So sometimes you see this on your computer screens and things, you may have seen that term. But for example, a 16:9 ratio is a widescreen TV, and most of your laptops use that ratio. So that means if it's width to height, for every 16 centimeters of width, you would have 9 centimeters of height. So it's much wider than it is high. A square, like a perfectly square TV or a perfectly square laptop, would be a 1:1 aspect ratio. So, quick little activity for you. I want to use what you've got lying around, some rulers, bits and pieces. I want you to find the width and length of some of the devices in the room and find their aspect ratio. So check whether your laptop, for example, is a 16:9 ratio. You could have a look at the TV on the wall. Is that a 16:9 ratio? Even your phone, perhaps, which is in your locker, but you could potentially get it once you've done the other two, and check what is the aspect ratio of your phone. The phone's a little bit tricky because you can change the orientation. So given that it is generally designed to be read upright, it's not going to have a wide screen, it's going to have the opposite. It'll be more like a 9:16 ratio, but it'd be interesting to check. The next thing we look at, and I hinted at this earlier on in the video, is this concept of stoichiometric ratio. So it's a cool little word. And the stoichiometric ratio is 14.7 to 1. And this is really the sweet spot of a combustion engine to get the optimum amount of power. This means that you need 14.7 parts of air for every part of fuel that you're putting into that engine. Let's consider the A-10 Warthog fighter, which is the background image of these slides. It uses about 2,300 litres of fuel in just 50 minutes of flight. So what I want you to do is use this information and calculate the amount of fuel that it would use in 1 minute. Then use the stoichiometric ratio to calculate how much air it would need in a single minute of engine time. Obviously, air is not litres, so we can't really do that perfectly, but let's just treat it like that. We know it's not a liquid, but your answer can be in litres. So how many litres of air would we need in 50 minutes for this thing to run? And these are real facts. I actually looked this up. This is how much fuel it uses. It's a very thirsty beast. Another real world ratio. This is a problem I actually had the other day. My chainsaw uses a 50:1 mix of petrol to oil. So 50 parts petrol, 1 part oil. Unfortunately, the only thing I could find in my shed that had any kind of measurements on it was a 600 ml bottle, and the only little oil container I could find only gave me 10 mils. And it took me a bit of time to think about ratios and how the heck I could figure out how to accurately mix my bottle. So I want you to do the same thing. I want you to figure out, using those two measuring devices, how could I accurately mix a 50:1 ratio with what I've got? So that's a bit of a challenge for you. I want you to think about how you do it, write down the answer, and come let me know to see if it's the same way that I did it. Time for our success check. Question I want you to ask yourself now is, can I calculate the actual length and drawn length of an object if the scale was given? Can I draw an object to a scale? Can I convert between drawn lengths and real lengths if I know the scale of an image? And can I calculate the scale if the drawn and real lengths are supplied? If the answer to any of those is no, or you're not confident, just go back and double check some of the questions related to that statement. Ask the person next to you to explain it or to make up an example for you to test, or come speak to me and I'll explain it.